Okay, this is your Chapter 14 Introductory video, Part 2. And for this video, of course, this is the outline and what we'll be doing, what you see in blue. Here, we've done everything else in the first video. And the red here, I've designated this is something that we're going to want to spend a lot of time on, both in the video and at home. It's going to be a very important section. So these were the learning goals, and the ones down here in red are actually what you're going to be dealing with here in this video in the second half of Chapter 14. So we have Le Chatelier's principle, something I introduced the idea of before, and that is a system at equilibrium responds to a stress in such a way that it relieves that stress. So what is actually a stress? When we say a stress, we kind of mean like something that's going to shift the system from equilibrium. It's no longer going to be at equilibrium. So effectively, you would say that once you apply that stress, Q is no longer equal to K. Remember what Q is. Q is calculated the exact same way of K. However, Q can be calculated at any point along the course of a reaction. K only holds true when its only value is only significant or defined at equilibrium. So there's only one value of K, but there's infinite values of Q, effectively. So imagine a reaction of A plus B going to C. Now you can think of it like this. Remember what the equilibrium constant is. In this system's at equilibrium, we say it's the concentration of C over the concentration of A times the concentration of B. If I were to add more product to the system that is at equilibrium, so I'm going to add some more C, what happens? Well, you can see that effectively the numerator increases, and therefore Q is no longer equal to K. In fact, now Q is greater than K, and we learned this in the previous section. If Q is greater than K, well then effectively you've got to decrease the amount of products and increase the amount of reactants. Effectively, the reaction is going to shift in that direction in order to reestablish equilibrium. So that's basically what we're realizing here, is that we're just shifting the system from equilibrium and it's going to respond. Another way to look at it is, hey, if I add more C, the system's going to want to consume C to reestablish that ratio that is the equilibrium constant. So it has to consume C, and in the process it forms more A and B. So that's the basic gist there of Le Chatelier's principles. Other ways in which we can introduce a stress also. But this is an easy way to start out talking about Le Chatelier's principle. Effects of adding or removing reactants or products. So effectively, I've shown you this already. Now, if I were to remove CO2, let's take an example now where I'm actually going to remove CO2. My question is, what's going to happen? Well, the system's going to react to replace the CO2. Effectively, the reaction moves towards the right. You can think about it in terms of mathematically, what's happening to K when it's no longer now K, it's now Q, and what happens mathematically. Or you can think about it as the system just kind of responding to kind of counteract what it is that's been done. Another example would be adding H2O. If I add H2O, what's going to happen? Well, if I add H2O, the reaction also shifts to the right. Well, because it wants to consume H2O now, which is over here. In order to consume that, it's going to have to produce more products. The key to realize is that the equilibrium constant value has to be maintained. So let's say your equilibrium constant is 10. If I now add H2O, it has to reestablish the ratio of reactants to products to reach 10 again. And then that's when the system will be back at equilibrium. So in this case, we're just saying, okay, this should be a bit redundant, but if you add A or B to the system, so effectively to summarize, if you add A or B to the system's going to react and shift in this direction. If you remove A or B, should have done that in a different color. If we remove A or B, then the system's going to react and go in that direction. Okay? Now let's explore a little bit more here. Changing volume or pressure in a gaseous equilibria. So, let's say I take my volume now. This particular system's at equilibrium. Take my volume and I'm going to double it. Well, you can start to think about what that is in terms of concentration. And you're looking at this here. And let's say these were initially at the same concentration. And we'll just use arbitrary numbers. We could say 1 over 10 and 1 over 10. They're at the same concentration. Remember now, though, this one's going to be squared in the numerator. It's going to be 1 over 10 squared over 1 over 10, if you will. Effectively, it's really what we're looking at. Now, if I double my volume, this becomes 1 over 20. This becomes 1 over 20 squared, right? So this concentration now is less. This concentration here is less than this one. Effectively, what does the system need to do? It needs to move in the forward direction to replace that concentration and reestablish equilibrium. So another way of looking at it is there's two molecules here. If you double the volume, you lower the concentration. You lower the concentration. The system responds by wanting to increase that concentration and moving towards the side that has more molecules, 2 versus 1. There's two ways of looking at it. You look at it mathematically as a concentration. You can look at it in terms of molecules. Now, I've mentioned up here, this is, volume and pressure we're talking about, but the only way to change the pressure effectively, if you look at this, the only way to really change the pressure is without changing the numbers of molecules and without changing the concentration. You have PV equals nRT, right? And without changing the temperature, because the temperature changes the equilibrium constant. So we can't change the temperature. And we won't want to change the number of particles, because that changes the concentration. That's basically the same thing we just did up here. That is changing the number of particles. So the only way to change the pressure then is to change the volume. Okay, well, actually up here we actually changed the volume. I'm sorry. The previous slide we changed the number of particles. So if you actually want to change the pressure, well, if you want to increase the pressure, well, then what do? You half the volume. So if you want to double the pressure, you half the volume. So the reasoning is the same as up top here. In this case, I'm going to want to remove molecules, because if I half the volume, the concentrations are increasing. And now, in this case, I'm going to shift the reaction back in that direction, go from 2 molecules to 1 to relieve that pressure. Another way to think about it is relieve that stress. There's two ways to think about the pressure and volume scenario. There is one thing to realize, is that P and V changes have no effect if the change in gas molecules is 0. And that is, we have 2 on this side, and we have 1 plus 1, 2 on this side. So if you were to half the volume, or double the volume, or double the pressure, however you want to think about it, the system can't respond to correct it. And you realize what happens is, the reason it doesn't have to respond is the equilibrium constant doesn't change. Because effectively, this is, if they're all the same concentration, once again, if you can use 1/10 as a concentration at equilibrium, this becomes 1/10 squared, or 1/10 times 1/10. This becomes 1/10 times 1/10. If I double the volume, it becomes 1/100th by 1/100th, but you're squaring it here on this side, and you're multiplying it by there at the same time. So mathematically, the equilibrium constant doesn't change. That's the beauty of understanding it both from a mathematical perspective and from a conceptual perspective. Another thing to note is that if I add an inert gas, and that is a gas that's not involved in the chemical reaction, so here I am going to add argon to the system. Well, nothing happens. No effect. Why? Because argon's not involved in the reaction. So effectively, the pressures of these gases is unchanged, even though you're adding argon, because you're dealing with individual pressures, if you will. That's what Dalton's law of partial pressure tells us. Kind of independent of each other, so that we do not have to worry about a gas that's not involved in a chemical reaction, so it does not affect the system at all. Now, of course, if you change temperature, you effectively are going to change your actual equilibrium constant here. And it will depend on whether the reaction is endothermic or exothermic. So this reaction here is, of course, endothermic. And what that means is that heat is effectively on the reactant side, right? It's being absorbed. So what we see is that here is Kc increases with increasing temperature. And that makes sense, because what we can say is that, okay, just treat it like Le Chatelier's principle, just treat heat as a reacting species, if you will. If I add more heat, the system responds by moving in that direction. That's the easiest way to think about it. Okay, we described it other ways in saying, that for an exothermic reaction, if you have heat on the other side, so it's going to reverse in the opposite direction. We think of it as it's more difficult to give off heat if it's already at a high temperature. If you increase the temperature more, that becomes basically part of the products, makes it more difficult. So in this case here now, we can just say that if temperature's increased, if it's endothermic, we just said if it's endothermic, which it is, it's going to move in this direction. Its heat is reduced, it's going to move in this direction. That's just summarizing basically what we just said. You can do the opposite then for an exothermic reaction. Okay, so now we need to talk and spend some time on Rice tables, and this is a big section, and you're going to need to spend a lot of time on this, and we'll do a lot in class also. So what Rice stands for then, I think I mentioned this in class already. R is for a reaction, I is for initial concentration, C is for change, and E is for equilibrium. We're going to use this concept to just dive in and talk about a problem. So in this case, is what we're dealing with known Kcs, and we're asked to calculate concentrations at equilibrium. And here's the particular problem now. We're told certain amounts of material in a volume of a flask, and we want to know what the concentrations are at equilibrium, and we're actually given an equilibrium constant. And the temperature is given. We don't need that in our calculation, but that's going to be given, of course. So remember what we did in class. Now we've got to fill out our Rice table here. So do you say what we started with, what was given to us was, let's see, I think it was 0, right? 0 and 0.0500. Now, so in this case, we're actually starting with all product. So that means any change here has to increase. So we think of this as plus x. And this is exactly the same. They're a one-to-one relationship. So this is going to be plus x also. I'm going to designate that as x, which means this has to be decreasing, also has to be decreasing by a factor of 2. That makes this minus 2x. Now your equilibrium part of your table down here is just adding up these two columns. So effectively, your equilibrium concentration here is x. Equilibrium concentration here is x. Equilibrium concentration here is 0.0500 minus 2x. Okay? So now you can write your Kc. My Kc is equal to the concentration of the products squared over the concentration of the reactants. Right? Now I could substitute this in. I could say that's 0.0500 minus 2x over x times x, basically, right? X squared. And we know that Kc is equal to 76. We were told this in the problem. So now I can write this and say, and I'm going to bring the x squared over here. I'm going to cross multiply that. So I'm going to say 76x squared is equal to 0.0500 minus 2x. Okay? So now we have the equation that we need to solve. Oops. I made a mistake. I made the classic mistake that everybody makes. And I made it unintentionally, so beautiful. This is a good teaching point. What I'm going to show you here is the fact that I used the 2 here, but when I write the equilibrium expression, I wrote this here, but I forgot to square it. Okay, just because this is designated, this is just your algebraic expression for the change. You still have to take this right here and plug it into here, which means it has to be squared. So I caught my mistake, which is a good thing. So this becomes squared over here. Okay, good. Now, so what we have now that I've corrected that mistake, we have 76x squared equals 0.0500 minus 2x squared. Now, if you're good at solving algebraic expressions, the first thing off the bat you're going to say is, okay, let me take the square root of both sides. And that's what we're going to do. So I'm just going to go like this just so you realize what I'm doing. Square root of this and square root of that. So basically we get 8.718x, that's the square root there, equals, and that's going to be plus or minus because there's 2 roots to this, 0.0500 minus 2x. Okay, now I'm going to solve this, and I'm going to use it by both plus and minus. So when I do that, I'll wind up with 10.718. So I treat this as plus, and then I bring that over here. I'll be adding it. Okay, if I treat this as plus, so the first thing I'm doing is treating this as a plus. And if I bring that over here, then you get this 10x here is equal to 0.0500. Or, if you will, let's do the negative root. And this now becomes 6.718x is equal to 0.0500. And that's actually a negative there because it's a negative root. Those are your 2 options. So when you solve this then, you wind up with over here, x is equal to 4.67 times 10 to the minus 3. And over here you wind up with x is equal to a negative 7.44 times 10 to the minus 3. Now, remembering what x is, it makes absolutely no sense to have a negative concentration because that's what x is. So we could effectively ignore this negative root. So that means this is our value of x that we use. That being said, we now have 4.67 times 10 to the minus 3. We now have, filling that in, we can say H2 was equal to x, which is equal to 0.00467, and this is molar concentration. This was also equal to x, so that's going to be the same thing. And this was equal to 0.005. Oops. Wait a second. No, it's 0.05, right? Yes, not 2 zeros, sorry. 0.0500 minus 2x, which winds up being 0.0407 molar. So, one thing that's always a good idea, check your work. And what we want to do by that is just simply saying, okay, let's see what Kc equals now with these numbers put in. Because we know it should be hi squared over h2 times I2. That simply becomes, put the numbers in, hi's down here, 0.0407 squared over the other two times each other. 0.00467 just times each other. So it's basically squared. That winds up being 76. Effectively, yes, we're good. We have checked our work. Our concentrations seem reasonable. The last thing in this video is, real briefly, we're going to spend some time on this in class, and we'll do more Rice tables in class, of course. Equilibrium and thermodynamics. Free energy, delta G, determines spontaneity. That's what determines spontaneity. When delta G reaches 0, you're at equilibrium. Delta G and Q are related by this equation. Delta G is equal to delta G naught plus RT natural log of Q. Free energy changes as the quantities in the reaction mixture change. That's what this is telling you. So as my reaction mixture changes, this changes. This does not. This is simply based on the difference in your reactants and products, but not at any particular concentration at any time in the reaction. Okay, standard free energies are calculated based on 1 molar concentrations. It's kind of like a potential energy determination. The difference in, those spots on the graphs that we talked about spontaneous reactions, things like this, is the difference between here and here. Where delta G, that's what we're graphing here, is G. G is all along this line. That was one of the key things we had to distinguish. And we'll spend some time on that in class. So, once a reaction has reached equilibrium, what happens is basically Q equals K, right? Delta G equals 0. Hence, the reaction on this slide becomes delta G naught is equal to a negative RT ln of K. So the equilibrium constant is directly related to the free energy change. And you can say effectively, if the free energy change is negative and you've got something like this, right? Well, what does that tell you? Equilibrium lies heavily to the product side. So a large negative delta G equals a large equilibrium constant. And that's one of the keys to understanding thermodynamics. This is a nice figure from your graph. We'll spend a little bit of time on this in class. Video is getting long here, so I'm going to wrap it up by saying that since K is related to delta G naught, it's also related to delta H and delta S naught. And these change very little with temperature for the most part. So we'll spend some time talking about that in class as our last section. And with that, I'm going to wrap up this introductory video here for Chapter 14, Video 2.